So thanks very much for joining. This is actually the last Symmetry Seminar before the summer. We take a break and we restart in September, October. So it's great to have Michael Gutperle from UCLA, and he'll tell us about non-invertible symmetries in SN orbifolds. Please take it away.
Okay. Yeah, thank you very much for the invitation. Yes, so I'll talk about non-invertible symmetries in SN orbifolds, symmetric orbifolds, and this is based on two recent papers, which appeared in May and in June with two graduate students from UCLA, Yan Lee and Dikshant Rathore, and then an ex-postdoc who is now at Hopkins, Kostis Rumpadakis. So, here's the outline, and I hope, I'm a bit rusty with Zoom talk, so we'll see about the timing. So I'll start with an introduction.
Yeah. You can take your time.
Okay, yeah. All right, okay. So I switched from 1.5 to 1.0 speed or so. So in the introduction, I'll review just some background material on non-invertible defects in rational conformal field theories, and remind you about some facts about symmetric orbifold CFTs. Then I'll talk about the construction of our defects and contrast them with some other constructions which have also recently appeared in other papers. Then I'll talk about using the modular invariance to determine, which defect operators exist, or what meaning about operators on which our non-invertible defect lines can end. I'll give a little example. It's not, there's more of that in the paper, but just the simplest case where there are non-invertible symmetries, namely the S3 symmetric orbifold. And then as an application of these defects, I'll talk a little about the calculation of entanglement entropy in the presence of the defects, which is sort of a nice observable, which one can calculate in the CFT, which also, might obviously have a dual description when we talk about the holography. And then lastly, I'll talk a little bit about a proposal for a holographic worldsheet dual in the Neveu-Schwarz ADS3 times S3 times T4 background with 1 unit of NS flux. And then I'll summarize and have a couple of open questions. And please, at any time, interrupt me. Okay, so I guess this is probably familiar to everybody here, but I'll just quickly review that one of the best known examples for non-invertible symmetries exists in two-dimensional rational conformal field series, namely the Verlinde lines. And so here I'm taking sort of the simplest example of a RCFT where I'll have where I labels the chiral primaries of the chiral algebra, and here I might just focus on, say, rational sorry, just a Virasoro algebra or so, but this can be generalized where I have like a diagonal partition function. And then one formulation of these defect operators due to Petkova, and I'm sorry, I guess I had a misspelling here, Petkova and Zubair as projectors is uses the modular S matrix, and the defect is written as a projector on the module, label, which is labeled by the chiral primary I. What happens then is that using the property of the projectors and the modular S matrix, namely the Verlinde formula, one can show that these defect operators have a non-trivial fusion product, and that the fusion coefficients are exactly the fusion coefficients of the chiral algebra expressed in terms of the S matrix via the Verlinde formula. So one thing, a slightly different or alternative formulation of this, which I mean will be useful a little later, is the construction of these defects as a Z2 permutation brane. And I mean, this goes back to a paper by Recknagel. I should say that I'm really not very thorough with references, so I apologize already. So the idea here is that when you have a defect, we can look at the left and the right CFT, and we can fold it where, I mean, we'll basically do a worldsheet parity and a construction of a conformal defect, or I mean, more especially a topological defect, can then be given by a boundary state in the folded CFT. To get a topological defect, one basically, I mean, which would be the equivalent construction of what we had on the previous page, is given by taking the Ishibashi states, where I basically sum, I mean, over the primaries and then all the descendants in the way. And here I'm basically then exchanging the first and the second CFT. So if this would be 1 and 2 here, this would be basically a completely separated defect. But when I make this C2 permutation, the boundary state satisfies the following properties. I mean, where the Virasoro modes basically, I mean, has the sort of usual behavior, but now basically with L1 and L2 bar and L2 and L1 bar. And that's basically when you unfold, go back to this, then this actually is equivalent to the fact that this defect then is topological. Namely, it commutes with the chiral, the holomorphic and the anti-holomorphic modes of the Virasoro algebra separately. And this has to do with the fact that this folding has a worldsheet parity, which actually exchanges the barred and unbarred modes for the second CFT. And then what one can also convince oneself is that Petrova and Sauveur, I mean, in their paper also developed the consistency conditions for these defects written as projectors. When, I mean, basically to do with modular invariance when I insert them, and then these consistency conditions are equivalent to the Cardi conditions for these boundary states. So viewed viewing the defect as a boundary CFT in the folded theory. So this is sort of the review about the topological defects in RCFT. So now I'll just do like 2 slides, just recalling some facts about the symmetric orbifold. So the symmetric orbifold construction, I mean, is a very useful construction to basically get new CFTs. So what one does is one takes an n-fold tensor product of a seed CFT M, and then one basically mods out gauges, I mean a discrete gauging or an orbifolding with Sn. And so I mean this is useful because there is a notion of a large n limit where one can basically have the idea of a large n factorization, the analog of what would be in gauge theory, single trace operators, etc. But it's also like, I mean, even for finite n, a way of constructing a new CFT from old ones. Due to the gauging, what this means is that in the untwisted sector, one has to project the states into Sn invariant states. So say for if this label I labels the copies, we'll just sum over all of them, etc., so that this becomes invariant under Sn. So it's a projection onto Sn invariant states. But I mean, as it's well known, if you then have if you move an operator around a twisted sector, which is necessary for modular invariance, then an operator can close only up to an action of G. And again, as is well known, that the twist operators, I mean, are not labeled by a group element, because such a twist operator would actually not in itself be Sn invariant, but by the conjugacy classes, which would basically be constructed here. So conjugacy classes are basically labeled by partitions of n, and the interpretation of basically this is that here I have, I mean, as you know, permutations I mean, can be labeled by basically the number of cycles. So the number of 1 cycles, 2 cycles, etc., where obviously then this condition has to hold. So when I look at the torus partition function, then basically it will be modular invariant, and what happens is that I will sum over these sectors where G here basically labels the twisted sector. So this is a sector twisted, I mean, in the G twisted sector, in the conjugacy class of G. And then the projection onto Sn invariant is basically given by the summation of H, which ensures the projection onto Sn invariant states. And I mean, the fact that a certain combination is basically trivial on the torus leads to the condition that G and H actually have to commute. So one way one can think about this is that H has to be in the centralizer of G. So in the twisted sector, we will basically have the modules are built on acting on twisted sector ground states with, say, fractional Virasoro modes and dimension of, say, a general twisted sector ground state is basically given by this. In the following, we will mainly just look at the example of a conjugacy class or a twisted sector, which is simply a single cycle of a certain length. So where the formula becomes simpler. Okay, so now I will talk about the construction of the defects. And so the way this works is that we'll can use this permutation brain trick. I mean, so we have the folded CFT, I mean, which is the tensor product of both factors. And then we indeed basically use this Z2 permutation trick as before. So we sum over all the twisted sectors, and then we'll have basically the module built, I mean, these Ishibashi type states built with acting with all the Virasoro modes and fractional Virasoro modes. I mean, here just denoted by the sum over M and N. And just as in the RCFT case, we'll have the boundary state by construction, I mean, satisfies the same condition, which is equivalent to the statement that the defect is topological. So the what labels these defects is indeed the representation of Sn, because what I'm putting in here is simply the character of a given representation. So our defects are labeled by a irreducible representation. I mean, if these are simple defects, R of Sn. If I unfold, then I mean these defects can again be written as projectors. I mean, where I'm not really writing out these projectors, but basically these would be projectors which act as the identity operator basically in the G twisted sector. So these are our topological defects. So what one can show is that if I again, one can use the form of the projector and the properties of the character, that these topological defects have again a fusion product, where if I take two defects labeled by two irreducible representations, the fusion involves the Kronecker coefficients, which are simply the coefficients which give me the decomposition of the tensor product of two representations, R1 and R2, into irreducible representations. And since as the symmetric group, for n bigger than 2 is non-abelian, this clearly will lead to a non-invertible symmetry. And I remind you that these n's could be written basically as sort of a triple sum of the three characters of R. Another useful feature of either from the projector or the boundary state is that one can look at the action of this defect, say, on the ground state or on actually any ground state in the twisted sector. This would be the ground state in the untwisted sector, which is the state, at the lowest conformal dimension in the symmetric orbifold. And what one finds is that, the ground state is identified with the conjugacy class just of the identity. So we get the character of the identity here. And this is simply from basic finite group theory, this is simply the dimension of the representation R, which one could then basically identify with the quantum dimension of this operator. And therefore, from SN representation theory, it's clear that the dimension, of any representation other than the trivial and the alternating representation of SN are bigger than one-dimensional. And again, that's based, so basically these two facts tell us that indeed these defects will realize a non-invertible symmetry on the symmetric orbifold CFT. Okay, so I wanted to maybe talk just a little bit about other possibilities to construct defects. So, we called these defects universal, and basically this comes from the fact that in each twisted sector, in each sector of the CFT, basically these projectors, which I'm using to construct the defect, act as the identity. And so, for example, if I just look at the untwisted sector, I would have an n-fold copy of a trivial defect. Namely the defect which is simply the identity operator. Yeah, is sort of trivially a topological defect. So put it another way, as I said, our defects are simply labeled by the irreducible representation, so they're completely blind about the details of the seed CFT, yeah, which I use to construct the orbifold, and therefore, they only depend on the SN group theory data can be constructed, for any seed theory. So there are obviously other possibilities, and these have been discussed in a recent paper, but by Knighton and collaborators in greater detail. Basically, what I would call a non-universal defect is something where obviously one could also say that what if I start with a non-trivial topological defect in the seeds theory, and can this be lifted then to the SN orbifold? So one thing which has been worked out in some detail, yeah, a little bit by us and a little bit by much more by Knighton and collaborators, is the sort of maximal fractional defect. This name comes basically from an analogous construction, which was done before on D-branes in the symmetric orbifold. And so basically the idea is that one takes a single topological defect And so basically for this, yeah, and here I'm limiting myself basically to one, I mean, in a rational CFT. So basically I can construct using the boundary state, yeah, in a W twisted sector, basically sort of combine the construction of a Verlinde line with I mean, basically construct a boundary state associated with an RCFT defect in the W twisted sector. So basically, what this means is I'm distinguishing now the combinations, the linear combinations of the different primaries, yeah, and weight them by here. So if I take A equals 0, yeah, I would be back basically to my original construction. Maximal fractional then basically means I have to obviously make this as n invariant that I then basically take this defect, yeah, say labeled by the chiral primary label A, and then basically take the same defect in all sectors and take the product. And so it has been shown that basically that these construction, yeah, satisfies the Petkobar-Subert I mean, Cardy-Petkobar-Subert condition, and therefore defines a consistent defect, which basically combines the defect in the seed CFT with this idea of basically taking the group theory data to make a defect. Now, basically, one could also say, well, there is probably more complicated, more general constructions, yeah, because but these have not really been worked out for the defects in the CFT. Okay, so basically, from now on, I will focus on the universal CFTs. And so basically,
Can
one
I
of
just
the
ask
things
a
that happens, I
question
mean,
before you go there?
Yeah, sure,
So,
totally.
so mind you, if you start with a rational CFT, you know that it's Virasoro rational, so it's a minimal model. You have all the boundary states, and so also you have all the topological defect lines. But when you do this sort of SN orbifold, what is the chiral algebra? It's some kind of SN symmetrized version of Virasoro, and then do you know whether
Well, I mean, so
the
basically,
construction of
yeah,
these defects is sort of a complete set? Is it?
I think I don't think these maximally fractional ones are not I don't think they are a complete set. I mean, in principle, I mean, in the symmetric orbifold, I mean, here basically I wrote a topological condition really just for the say the Virasoro or the stress tensor, which is basically the sum of all the
diagonal,
copies.
right?
In principle, I mean, you also have, I mean, all the different factors, which means in some sense that you have, I mean, like a much bigger chiral algebra.
That's right. Yeah.
Of which, and I mean, these states satisfied, I mean, are in that sense still rational in the I mean, in this enlarged chiral algebra, but I mean, I'm pretty sure that for you know, like in say for the RCFTs or so, to get a complete basis, you would probably also entertain things where you would have actually used different defects, yeah, and then make them as an invariant. This wouldn't be the sort of maximal fractional ones, I think.
Okay, right. Thanks.
Well, I think there was a paper by Bellin and others, I mean, in the deep brain case, where they sort of like discussed this a bit, but I don't think it has been. I mean, the deep brain case is a little different. I mean, because there's basically, I mean, it's folded, but it's not really the product of really two factors. I mean, you're basically constructing a BCFT just in a
given bulk theory,
yes. In a given one. Okay.
Okay, thanks.
Yeah, so obviously, one of the defining and interesting features of non-invertible symmetries is that you have operators on which a defect line can end, and this is what I would call defect operators. I mean, there's too many defects floating around, but that's sort of what I mean. And the way we can get at them, I mean, and this has been done, I mean, in the RCFT case, and we're basically doing the same here, is that you use modular invariance. So that, I mean, we'll have basically, say, on the torus, I mean, we'll have first the insertion of the operator along a spatial circle. So which, I mean, here, say if this would be 1, I mean, this would just be the partition function. So now I insert the defect, and this modifies the partition function. And so basically what will happen, I mean, because our defects are simple and only involve basically this sort of weighting by the character, I mean, then I will basically have here just the character of the representation R, which labels the defect. I mean, oops. Sorry, I don't know what happened. Sorry, I'm apologize. Labeled by the character. So we'll get to the defect Hilbert space by making a modular transformation, which basically will lead to the insertion of this defect along basically the Euclidean time circle. And I mean, basically, what you can also recall is that basically the under modular transformation, basically I mean, each sector will go basically the twists along the space and the time circle, I mean, get interchanged. There's a g to the -1 here, but basically the reality of the I mean, there's in for Sn all the characters are real, so that actually doesn't really matter. But so basically, to get to the defect Hilbert space, we'll do a modular transformation, and so basically, what effectively happens is that G and H get interchanged. And so I remind you that basically in the original one, or for the insertion in the spatial direction, I mean, G labels the twisted sector state, and H is basically the centralizer, or all the elements which commute with G. So for the modular transformation, I mean, G and H are exchanged, and so one could still. So basically, what would happen is now that the twisted sectors are labeled by H instead. And what one so what does it mean to look for the defect operators? So basically, I mean, we don't make this analysis in general. We simplify basically to look at the operators which are basically have the same in this partition function, which have the same conformal dimension as the twisted sector ground states in the orbifold. So in the simplest case, where the conjugacy class G is a single cycle of length W. This is again, I mean, I guess a simpler version of the general formula I had in the review. That the conformal dimension of this operator is given by the seat central charge, and then basically by this formula. So, I mean, one way of thinking about the defect operators is, I mean, through, say, a lasso effect. And so where I would basically have a twisted sector and a defect, and I move them past each other, and then we will have a defect operator ending on this. Now, basically, because these defects are topological, that means that the conformal dimension cannot change. I mean, so in this in this process, yeah, a defect operator here would have to have, I mean, the same conformal dimension as our twisted sector ground state. So basically, the challenges that we're looking for, whether these states, I mean, given in a given site, in a given conjugacy class, appear in this partition function. So again, we're not doing the most general analysis here. Just for simplicity, we'll basically look at the conjugacy class where we have a fixed W cycle. But basically, I mean, remember that H now labels the conjugacy class. So G is in the centralizer of a single W cycle, which basically means that what are the elements which commute with a single W cycle? I mean, it's basically Sn minus W. I mean, meaning the permutation of all elements other than the W elements, which I mean get cyclically rotated. And then I mean, since basically the and in addition we have a basically just a ZW cyclic rotation of the W elements. So what that means is that we can basically write, I mean, in the full partition function, we will basically then limit ourselves to the contribution of the W, the W cycle twisted sector. And so one can write this out. Yeah, so this would basically be the W twisted sector, and then we'll sum over the centralizer. So here G is basically in the Sn minus W, and then we also have, I mean, basically the action of the ZW, I mean, which is say 1, and then omega k to the, I mean, meaning basically the different powers of the kth use of unity. And then in this partition function, we look basically for the terms which are associated with the ground, with the twisted sector ground state. Yeah. So basically, I mean, what you realize is, as far as the Sn minus W is concerned, yeah, I mean, we're basically in the untwisted sector. I mean, because the twist is really just the cycle of the cyclic. I mean, the cycle acting on W, the first W elements, and then in with respect to the N minus W elements, it's in the untwisted sector. So all these states will basically have a unique ground state, I mean, with a zero scaling dimension, because that's the ground state in the untwisted sector. Yep. For the twisted sector, we can basically work out the contributions, yeah, from just the partition function of the seed, the seed CFT. So what happens is, I mean, that we'll basically have sort of this fractionalization, I mean, of the modes, and then a sum basically over K, which is basically giving you the cyclic permutation of omega K. Now, because I mean we are basically looking here at effectively like a diagonal partition function, this sum over K actually cancels out between the holomorphic and the anti-holomorphic parts for the ground state. And so we will basically look at at this contribution in the partition function. And so what this means is that in all of these factors, yeah, basically the contribution to the ground state, I mean, for excited states, this will not be true, but we're just looking for the twisted sector ground state here, will all be the same. And basically that the multiplicity is then in each term is given by multiplicity 1. And so we'll simply sum up the prefactors. And basically what this means is that this will give us, this function, this number will give us basically the multiplicity of the defect operators with the same scaling dimension as the twisted sector ground states in the W twisted sector. So in general, I mean, you know, basically this is kind of complicated because we have this sum here over the Sn minus W, and I mean this character. But say, I mean, one can do this sort of by hand without using a computer for the simplest case, which is S3, which I wanted to review now quickly. I mean, this is probably very familiar. Yeah, it has 6 elements. Then we have the identity, 3 2 cycles, 2 3 cycles. And then we also, I mean, there's again a fact of finite group theory. We have 3 irreducible representation. I mean, the trivial representation, alternating representation, and the standard 2-dimensional representation, and these are the characters. This is the fusion product, and I mean, then we see that indeed the defect associated with the standard representation is indeed non-invertible. And say basically, if one uses this character table and this formula, I mean, here there is actually then no sum over this. I mean, this makes it a little simpler. What one can find is that, say, for the alternating defect, basically there will be no defect operator in the 2-cycle twisted sector, and there will be 1 in the 3-cycle. And for the standard defect, there will be 1 in the 2-cycle and none in the 3-cycle. And this one can actually see sort of explicitly here, basically by looking at the partition functions of the seed theory. And here I'm basically I dropped the tau bar just for notational simplicity. This would be basically the untwisted sector, the 2-cycle twisted sector, and the 3-cycle twisted sector, just for the partition function. If I am, say, looking at the ZA, yeah, so I'm kind of just explicitly now calculate these partition functions with the defect inserted. Yeah, then I mean, basically what will come in is the characters. Yeah, and so basically, actually here the only difference is basically this minus sign, you know, basically from this character here. But then I have to do the modular transformation, and what I'll see is that basically I'll get this. I mean, with a little work, one can convince oneself that this is what one gets. And so interesting, basically, if you look at the 3-cycle, then we will actually have pretty much exactly the same partition function as before. I mean, so this means there is indeed a 3-cycle twisted sector ground state in here, which is in agreement, I mean, with basically that we'll have a defect operator where the alternating defect can end. On the other hand, for the 2-cycle, we'll basically get this minus sign here, and that is basically coming, I mean, from the minus sign here, and the modular transformation of this term. And this will actually project out the twisted sector ground state. And therefore there is no, I mean, and this is the reason why it's 0. One can obviously do much more, and in the paper we look at the sort of word identities and etc. But I guess in the interest of time, I wanted to just move on. I mean, in general, this is obviously kind of complicated. I mean, because the, I mean, you know, the representation theory of Sn, I mean, gets very complicated with large N. So I wanted to basically look at one application of the defects we have up to now, and that is the entanglement entropy. Yeah, and so I mean, I'll maybe be just very quick. I mean, so we have I mean, the notion of an entanglement entropy in a CFT. So I mean, this is the simplest setup. We'll take a CFT. We'll take a region A. And then we look at the reduced density matrix, where we trace over the complement of A, and then we look at the von Neumann entropy, and that it would basically be the entanglement entropy of which measures the entanglement of the region A with its complement. The way to calculate this is basically the replica trick. So one looks at the kth Renyi entropy, which is basically replicates this setup on a k-sheeted Riemann surface, where basically the surfaces, the replicas are identified at this cut, and then basically, I mean, it's well known that the entanglement entropy can then be calculated by the partition function. of the K-sheeted Riemann surface, and then taking this limit. So the general form for the entanglement entropy, I mean, for this simple setup, I mean, where I'm basically having the CFT in the ground state and one interval, yeah, is I mean, going back to Cardi and Calabresa probably, is given by the central charge. Yeah, here basically L is the length of the interval, epsilon is a UV cutoff. I mean, in general, there would be there can be a constant, and that is called a G factor, or it's basically e to the SA would be the boundary entropy. Now, in the case of a system, I mean, without a boundary or a defect, yeah, this wouldn't be physical, I mean, because it can just be absorbed into rescaling of the cutoff. But for systems with boundary or defects, the G factor, I mean, is physical, and it will, I mean, usually be interpreted as having to do with I mean, basically telling us something about the, I mean, the complexity or the number of degrees of freedom on the defect or the boundary. So basically, what I want to do is I want to calculate the entanglement entropy in the presence of the defects we've calculated. Now they're topological, so I can, in principle, you know, unlike I mean, say a conformal defect, yeah, that you would think that for a conformal defect the location actually matters. You might say here it doesn't matter at all, and that's not quite true. Yeah, so basically, what I'll have if I say take this as the interval A is that I haven't, so basically if I go back actually to conformal defects, there's two cases which I can calculate simply. And the first one is if I have, and this is not quite a symmetric, but if I'm basically, if I insert the defect symmetrically in the middle of this interval, that would be basically the symmetric defect. The other one would be if I insert it exactly at the boundary of my region A and the complement. And that would be basically, I mean, that's sometimes called then the entanglement entropy with the defect at the boundary or something like that. Yeah, for a symmetric defect, yeah, one can in principle fold this, yeah, use the folding trick, and then basically you would actually have the defect basically becoming, yeah, I mean, as we said, the boundary CFT and the entangling region, I mean, is in some sense basically symmetric. And so we'll have basically, then we could think of this as the entanglement entropy of a region just like this in the tensor product. So this would be basically then the entanglement entropy in the BCFT. And I mean, this goes actually back to like kind of maybe Affleck and Ludwig and has been used quite a bit. That, I mean, one of the users say of the boundary state construction, yeah, in this, say with this permutation brain trick, is that the G factor can then simply be obtained as the overlap of my boundary state. I mean, this is true for general BCFTs in this symmetric setup, as the overlap basically of the vacuum with my boundary state. And this has to do with then basically taking the fact that I will take this region L or the UV to be large, and then I basically, in a cylinder channel, I have sort of a factorization basically on the state of the lowest conformal dimension. So, but this is, so basically when one has a conformal or topological defect, which is symmetric, one can use this folding trick, and then basically one, this formula also gives me the entanglement entropy for the symmetric defect. So when we look at our boundary state, in permutation brane boundary state for our universal defect, this basically then allows us to calculate this G factor for the symmetric defect. And it's simply given by the character of the identity. I mean, because I'm looking here at the ground state in the untwisted sector. So again, this is the G, the conjugacy class of the identity. So I simply get the dimension of the representation or the quantum dimension of the defect. And So and then for this would be true for a conformal defect. What happens for a conformal defect is so that I cannot move it. And for a topological defect, I can in principle move this, and this shouldn't really matter. So for a topological defect, you can actually argue that it doesn't have to be really necessarily symmetric. So you might say, well, I can move it all the way to the boundary, but that is not quite true. There's something more interesting happens, and this is basically going back to a paper by Sakai and Sato, that basically the problem is that I have to still introduce a UV cutoff. And so basically, if I think about this here, that so here I would basically have a CFD, the interface is here. Yeah, basically my region A would be here. Yeah, that is basically it, that to calculate entanglement entropy, I have to introduce a UV cutoff, yeah, by basically epsilon, or cut out a small disk here. But this is exactly, where the boundary and the interface meet, and so that can lead to complications. So one way to calculate this is basically to use the replica trick, in the sense that we also introduce sort of an IR cutoff, basically basically at L, and then do a periodic identification here. And the replication then will basically be given by just using sort of an exponential map and basically going around k times. When I map this, yeah, basically, using the logarithm or the exponential map, what is happening is that if I use this periodic identification, this actually becomes a torus where I'm basically having the regions, yeah, of A and its complement, and then the insertion of the defects, and this gets replicated k times. Now, in the literature on like kind of say symmetry resolved entanglement entropy, one can do something more general. Yeah, instead of this periodic identification, one could insert like boundary states, and then the entanglement entropy will depend on these boundary conditions. But for us, we're basically using this periodic identification as sort of the simplest way of doing this. So the kth replicated partition function for the for the Renyi entropies then basically has this insertion of the defect and the conjugate defect, yeah, because I would basically the orientation of the defect kind of changes when I think about this replication, that I have to insert I and I dagger. So for conformal defects, obviously that doesn't commute with the Hamiltonian. For topological defects, I basically these defects commute, and I can just basically put them all together. And now in this cutoff and in this map, we would basically then have to identify the modular parameter of this torus, and it turns out that then basically it will be related, to the length of the interval and the UV cutoff in the following way. So if we want to calculate it, basically what happens for our topological defects, this replicated partition function becomes relatively simple. Yeah, we'll have basically just 2k powers of the character here, and then basically the same partition function of our twisted sectors with the with the SN projection. Now, if I take the limit, of either epsilon goes to 0, which would be removing the UV cutoff, or taking L to be large, yeah, because we're making a simplified, we're basically identifying L with 1 over epsilon, so that we're taking the limit L to infinity or epsilon goes to 0. But either way, this just simplifies the argument a little, that we're basically in the modular parameter, basically this means that tau goes to 0. So we have to use a modular transformation to evaluate this replicated partition function. And so again, as before, when we looked at the defect ones, yeah, basically H and G get replaced, and then we're looking at the limit where tau prime goes to infinity. So what this means is that that after the modular transformation, in this limit, this partition function is dominated by the states with the lowest conformal dimension, which is the vacuum of the untwisted sector. So basically, in this in this limit, which is tau prime to infinity, tau to 0, tau prime to infinity, basically we're completely in the untwisted sector. Now then, basically, I mean, here I'm running a little bit out of time. I mean, there are sort of more details in the paper. I mean, this projection, I mean, still leads to different partition functions, but it would be something, say, in the S3, I mean, it would be something like, say, c to the 3 tau and c to the tau cubed. I mean, we had these before. This is basically coming from, basically, like, say, the sum over S3 elements or so. But even what you can realize here is that basically the dominant behavior, yeah, of all of these, no matter what the basically this projection G is always given basically by the original, I mean, by the leading term, I mean, which is basically the behavior, the central charge of the symmetric product in the untwisted sector. So we can actually evaluate, say, I mean, easily the leading term of the logarithm of this replicated partition function, and so there will be basically this term, yeah, and but then there will also be basically, I mean, we keep the subleading term, but that is then simply this logarithm involving the characters. So if one then uses the form, which I mean the formula which gives the entanglement entropy from the Renyi entropies, yeah, I mean this 1 minus dk of log of z or so, one gets this following formula. So there is a universal one, and there's actually a 1/6, because what we did here is basically that we didn't have actually two boundaries. We kind of pushed one boundary to infinity. So that can actually be, that can explain this factor of 1/6. And we get basically a subleading term, so a constant term. I mean, this is ultraviolet divergent, as it should be. And this is the constant term, so this will be the G factor. And then one can basically use the orthogonality of the characters to get to this formula. So this is different, yeah, than the symmetric G factor, but this would basically be the G factor for a defect in the representation R. And I mean, here basically, I mean, this is sort of interesting because it looks a little bit like, I mean, if these characters were sort of probabilities, this looks kind of like a von Neumann entropy. I mean, what we've done is sort of basically look at, I mean, using this like gap finite group package just to calculate this for like larger values of n. I mean, so what we have here, I mean, I'll be quick because I guess I'm running a little low on time. I still want to talk about the holography. I mean, here we're basically having sort of the plot of the standard sort of ordering of the representations. I mean, which are for Sn given by Young tableaus. And say here, this figure is basically the one with the largest value of the G factor. Here we're basically just sort them by magnitude, yeah. And then I mean it becomes sort of, I mean basically there's a lot of representations, you know, for larger n. I mean it's sort of an interesting pattern, and then we'll basically the sorted one is this. I mean we don't really. I mean we thought a little bit about it. I mean this you know, I mean there's basically maybe an open question whether this is, I mean, whether there is sort of maybe a matrix model formula or I mean, representation of this, or whether one can really go to characters at large n. But I mean, we haven't really made any progress, but I guess it's kind of cute. Okay, so the last topic I wanted to talk about is a proposal for the holographic dual of these defects. So I just remind you that, I mean, there is a proposal for an exact duality of the symmetric orbifold, I mean, at the symmetric orbifold point, yeah, and that say basically when the seed CFT is T4 or K3, I mean, a supersymmetric sigma model, then, I mean, going back to the work of Gabadil-Kopakuma and Ebert, Gabadil-Kopakuma, a lot of other people, and apologize about the references, that there is a dual where we have type 2b string theory on ADS3 times S3 times F4 with 1 unit of NS flux. So this is very far away from a supergravity limit. I mean, this is a very stringy limit, highly curved ADS, but because it has an SNS flux and no RR flux, there is an explicit worldsheet formulation in terms of a Wessel-Minor-Witten model with a twisted M4 sigma model. I mean, this would be in the hybrid formulation. I mean, there are different formulations or so, but I mean, certainly like this duality has passed many non-trivial checks. I mean, matches of correlation functions, I mean, partition functions, D-branes, whatnot. And I'm obviously not doing it justice, but one of the things which happens is that there is an identification, and basically we're thinking about this in the large N limit. So where, I mean, basically there is a large N factorization in the Sn orbifold, means that the sort of single trace operators, which would be sort of the single string states, are associated with conjugacy classes or twisted sectors with a single W cycle. And so there is an identification basically that we have CFT operators in a single W cycle. I mean, here, I mean, in principle, one can do this 4 states, I mean, which have a non-trivial, you know, excited state in the seed CFT, but one can also do this basically, and this is the simplest for the ground state, I mean, in this twisted sector, and that there is a map, I mean, between the CFT operators and worldsheet operators, I mean, where, and again, I'm not writing the formulas here, but basically where the position, I mean, on the CFT side or the space-time boundary side, yeah, and this is the location of the vertex operator on the worldsheet. And I mean, going back to Maldacena and Okuri, basically the point is that this twist in the CFT is basically associated with the spectral flow. So, I mean, basically that we are in sort of a long string W, I mean, a sector of the CFT where we've spectral flowed basically by W, and the string kind of winds around W time. So the duality, I mean, sort of established, I mean, here is that basically we have an exact identification of the correlation functions, say of, I mean, n of these CFT vertex operators to basically a string path integral where these vertex operators are inserted, and in principle we integrate, I mean, over all worldsheets. Yeah, so this is a honest to God string theory path integral. But what happens is that, and this is sort of a special feature of this k equals 1 string theory, that there is a localization. I mean, that is string path integral in principle. We integrate over all worldsheets, I mean, of all genus, of all punctures, I mean, where like the moduli space also basically moves the punctures around, etc. But it is only non-zero, yeah, if there is actually a covering map from the worldsheet to the space-time. And what that means is, I guess I'll have to, sorry, I have, I mean, that we'll have basically a map of the worldsheet Z to the space-time X, and at, sorry, this is not good management of the figure, but that then basically at Z equals Zi, yeah, basically at this point in the worldsheet, this worldsheet gets basically mapped to the location of the vertex operator in the on the boundary, and around it we will basically have sort of a Wi. I mean, meaning this is for the ith vertex operator with like where we are basically in the Wi twisted sector. You have basically a ramification or a Wi fold cover, and so at leading order in large N, yeah, I mean, then basically we would, the string worldsheet, I mean, basically there is a relation between the string coupling constant and sort of 1 over N that will basically have a map of S2 to S2. I mean, so a spherical worldsheet map to S2. I mean, if we think about just global ADS, yeah, and and in general, this covering map doesn't necessarily exist, yeah, for all positions of even on the sphere to sphere, for all positions of the vertex operator in the string theory, and so it basically localizes on special points, and that basically reproduces the correlation functions. And that is very much basically what it reproduces is really this covering space method of evaluating correlation functions in the orbifold. So I guess I'll have to, I probably have, I mean, I have like 2 more slides really. So I hope,
Yeah,
I mean, if I get like 3 more
okay.
minutes,
2 more
is that okay?
slides is fine, yes.
Okay. So basically, for our proposal, we wanted to reverse engineer the CFT defect. So remember that we have the character here, projectors onto the G twisted sector. So in this limit, we're basically focusing just on the W cycle, I mean, the single cycle conjugacy class, yeah, because we're basically only looking at single string states. So basically, we'll limit ourselves to the sum over single cycles here. So one way of doing this is to consider the this localization. What happens is that one has basically a sort of free field realization, which is called a Wakimoto realization in terms of, say, I mean, these fields beta gamma and a free scalar field with a background charge. So this is valid at the boundary, but then remember this path integral, the string path integral, I mean, basically localizes to the boundary. And so one thing that was shown, I mean, in these papers by Ebert, Gabadil, and Gopal-Kumar, is that the string, string amplitudes, if I insert this field phi, localizes and basically can be exactly evaluated in terms of this covering map. And in general, basically, if I have a situation where I have, like, say, n points, I mean, with ramification wi, I mean, the Hurwitz formula basically tells us that, I mean, this is actually given by simple poles and then additional sort of secret poles on the worldsheet. I mean, which are basically necessary for this covering map to exist and be basically as 2-sphere to 2-sphere. So what we can do is we can then actually on the worldsheet say take a contour and define this operator simply as the integral, yeah, with the -2 of this free field. So if we insert it on the worldsheet, we can use the localization and simply evaluate it, I mean, for all correlation functions, because it's basically taken out of the string worldsheet. And so what happens is that if I take a contour which encloses just one vertex operator, then basically I'm only picking out, say, the ith vertex operator. I'm only picking out this residue. Yeah, all the others are somewhere else, and the secret poles are also somewhere else. So by residue theorem, I simply get basically for a contour which only encloses one, I get Wi minus 1. And so this means that at least we can look at the action of our defect, yeah, on a single operator would be given by the defect basically just encircling the defect. And then, I mean, because of this -1, it's a little, but basically what this means is that our worldsheet proposal then basically uses this operator Wi, and what it does, it will give, basically, it will reproduce, I mean, the basically that we get if we then basically deform this this contour and basically slip it off or bring it very close, then it will basically reproduce this I mean, this basic feature of the defect. I should also say that it has been shown that actually one in this operator I, or I mean, the property basically of this d phi is that it can be basically freely deformed as long as it doesn't cross any any defects or poles. I mean, which is basically just a function of this residues theorem.
Can you also
so
compute
in the paper,
can you also combine two of these and compute the fusion of them?
Well, I mean, so basically that is sort of so basically this is sort of the reverse engineering. Yeah, this is our proposal, and now one has to sort of see what happens. I mean, when I'm, for example, enclose
you have two
either
of these, enclose one point, but now you fuse them.
Slip it off. I mean, so basically what we have in some cases, I mean, for example, for the when it's invertible, I mean, meaning if I look at I mean, okay, for us, for our universal defects, the trivial defect wouldn't really do much, but say one can do it for the alternating defect, but that's invertible, then it kind of has all the properties which the defect should actually have. Ultimately, I think one thing which is complicated, but which I think is probably maybe to do if we want to reproduce something like a worldsheet representation of, say, a lasso effect or so, is really to understand the role of these secret poles better.
Okay. We should probably close now. Yes. Okay, great. Yeah.
Okay, so basically, I mean, I think for maybe just for open questions, I think there's obviously, like, I think it would be interesting to see about these non-universal defects. I mean, we had some comments sort of on the CFT side of large N, which I didn't have time. And basically, I think the open question is really whether this proposal makes sense. I mean, beyond this sort of simple reverse engineering, I mean, looking at the more complicated sort of ward identities, whether they have a worldsheet representation. And then also, obviously, like, I mean, we're in a very stringy regime, and we have this kind of localization property. So it's not clear like how this proposal can or is related to the kind of proposals of topological defects to do with basically branes in the bulk, which are sort of more in the sort of supergravity limit. I mean, basically with like non-topological branes in the bulk. But I mean, these constructions, as far as I understand, I guess you work on this too, I mean, are sort of on the limit, which would be like basically a large K, not K equals 1. But so I apologize for going over probably 5 minutes. But
yeah, great. Thank you. Yes. So some people left already, but thanks a lot for this nice talk. Are there any other questions?
Okay.
So I had one question, which you also mentioned here, which is the large N limit. So how much can you actually calculate? You showed like N equals to 35 or something. But do you have is there some sort of way you could characterize these things in the really infinite large?
Well, I think, I mean, there is obviously, I mean, there's one way, I mean, there is sort of in the math literature, I mean, there is a sense in which one can take sort of I mean, look at basically S to infinities and characters of this, and there are then formulas for basically the character of, I mean, in some sense it has to do with the basically taking the limit of Young tableaus, basically with like taking the number of boxes to infinity, where then we would have basically in some sense, I mean, what happens is that you would have sort of numbers, I mean, AI and BI, which are sort of smaller than, I mean, smaller than 1, and are sort of basically the number of boxes divided by N. But then there is sort of a limit in which basically there will some of these will be finite. And one has character formulas for this. So in principle, one can sort of, I think, work this out. What is not really known at all is basically then say, I mean, more complicated data, like say the Kronecker coefficients or so. I think this is completely open. So maybe the entanglement entropy, we could actually maybe say more about this. But then this is also something to do then basically that, you know, that maybe this smells a bit like that what we're actually having here is sort of something like a, you know, like a measure, I mean, on the S infinity, I mean, like something like a Blancherel measure or so. So, but what we haven't really, I mean, we thought about this a bit, but we haven't really come up with anything solid.
I have a question about the entanglement. I think we should stop the recording before. Are there any other questions? You know, some people had to leave, but if there are questions, please ask. I think I will stop the record. Thank Michael again, and I will maybe stop